these gas problems, and I hope that this video will help you. Now, do realize that not all of us are going to be using or needing to work out each problem, but if you need to fast forward through the video, please do so. Let's look at question number 1. It says, if compared under the same conditions, how much faster is argon than decane gas? Make sure that when you read the question that you understand which equation you should be using. Hopefully you're recognizing that there's a key word here. How much faster is argon than decane? And I'm even telling you in the question which gas is lighter, because it says that argon, it's asking how much faster is argon than the decane. So when you see a question like this, make sure that you pick it up and understand what the question's asking. So when you have a choice to use the equations, make sure that you're using the correct one. There's one equation that it just asks for the rate of a single type of gas. This one is comparing the two different types of gases. So let's talk about that equation. So the equation that we want to use here is this one, where we have the rate of gas 1 over the rate of gas 2, which is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Now, I've heard a lot of misinterpretations of what I've been saying because, again, I'm not sure what you're listening to or what you're working on while we're going over these problems. But when I say that place the lighter gas on top, I'm referring to R1. I'm not referring to the molar mass. Also, be aware that when you're working this problem out, be sure that you include all 4 components here. Don't just work with this part of the equation, because that's where a lot of people are getting in trouble. They're just ignoring the R1 and the R2, and they're saying, oh yeah, he said put the lighter gas on top. So you're placing the lighter gas in the place that it doesn't need to be, and you're getting some really weird numbers, and that's understandable. So when you see something like this, ask yourself which gas is lighter, and then make sure that we do that. Also, argon gas is a noble gas, but is it diatomic? Well, it doesn't end in gen or ine, so the answer is no. Decane gas is already written out for you, so you don't need to worry if it's diatomic or not. So let's go ahead and set this equation up. So we're going to place the lighter gas on bottom, which is argon, and then we'll put the heavier gas, which is decane, down below. So when we place the molar mass for argon, it is not diatomic, but it's 39.95, and that's grams per mole. Now, we do not need to convert the molar mass from grams to kilograms, because again, we have molar mass over molar mass. The units are going to cancel out. We're actually not going to have a unit when we finish with this. Then we need to find the molar mass for our decane. Well, that's all under the radical. So probably what I would highly recommend is before you plug or calculate for the value under the radical, find out what those values actually are. Well, we know that the argon is 39.95, but it'd be nice to know what that top value is. So the molar mass for the decane is 142.276, and again, that's grams per mole. Let's do a quick calculation. So I get 3.56. Now again, that's not my final answer. I still have it under the radical, so I need to take the square root of that value, and I get 1.88. Now, what my answer is telling me is a couple of things. First of all, it confirms that I actually have the lighter gas on top. Also, if I have the lighter gas on top, lighter gases are faster than heavier gases. So it's almost twice as fast under the same conditions. Okay? So again, to review, R1 is the lightest of the two gases. R2 is the heaviest of the two gases. We have the inverse of the molar masses, which again can be in grams per mole. Be sure that when you plug these in, you actually identify what R1 is. Don't just leave it as R1. Tell me what the gas is, and tell me what R2 is. Show me the masses, and you can go directly from here to here if you need to. There's nothing wrong with that. You don't necessarily need to show this step, but definitely need to show the answer. Let's take a look at number 2. The question reads, what is the volume of a sample of nitrogen dioxide gas that has a molar mass of 125 grams at STP? All right, first of all, make sure you know the conditions at STP. You have to know that. So at STP, okay, if you had 1 mole of any gas, doesn't matter what the gas is, because at STP they all behave the same way, you will have a volume, and that's our N, you will have a volume of 22.4 liters. That's going to save you a lot of time. Also, we know that the pressure is at 1 atmospheres, or if you want to do the conversion, 101.325 kilopascals. Also, it tells us that our temperature is at 0 degrees Celsius or at 273 Kelvin. Okay. Be sure that you know the conditions at STP. So knowing that we have these conditions at STP, we can really save a lot of time. Now, you can use PV equals nRT to solve, but here's the shorter way. So, start off with what's given. So we have 125 grams of our NO2. Convert your grams to moles. So 1 mole of your NO2 has a molar mass of, well, we have 14.01 plus 2 times 16, which is 32. And that is a molar mass of 46.01 grams. And then, what's nice is, if we're at STP, we know that 1 mole of any gas weighs, or has a volume of 22.4 liters, so move your unit mole down and put 22.4 liters. And that should give us 60.9 liters. Okay. All right. If you don't want to see this other way, simply fast forward through the video. I'm going to show you how you can solve this using PV equals nRT, which I know that some of you really need to be doing or using. So my answer, I know, was 60.9 liters, which we just found. All right, now we still have to use the 125 grams and convert that to moles. So I still need to do 125 grams. My molar mass for this was 46.01 grams, and again, that was for each mole. So we can solve to determine what our N value is. So 125 divided by, so I get 2.7, and we don't want to round too much, so we'll say 716 moles. Okay. And then we can plug our equation and solve for V. So we have PV equals nRT. We're looking for V, so that means that we need to move our pressure down. And so now our equation looks like V is equal to nRT over P. Then we can plug in our values that we know. Okay. Now, if you plan on using your P as 1 atmosphere, then we have to use the 0.0821 atmosphere liter mole Kelvin for our R value. So plug in the value that we just had, so 2.716 moles. And the R we'll use is 0.0821, and we'll call that atmosphere liter. And again, I'm a big fan of only one dividing line, so mole Kelvin. And then our temperature is at 273. And 1 atmosphere of pressure. Okay. And just to check, make sure that our units cancel out. So atmospheres are gone, kelvins are gone, moles are gone, and we're left with our liters. Okay. And I guarantee it's equal to that. Okay. So that's another way you could work it out. There's yet a third way you could work this out. If you're interested, stay tuned. If not, fast forward. The third way you could work this out is by using PV equals nRT and do it all in one step. In other words, remember or recall that PV equals nRT is our equation that we'll use. Also, recall that N is equal to little m over big M, which is equal to, this is the mass in grams, this is the molar mass in grams per mole. Okay, so we can substitute this in, and we can get the equation that looks like this, where we have PV equals little m over big M over RT by using substitution. And we're still looking for the volume, so we'll rearrange the variables so that we just have our volume all by itself, which means that we're going to divide by P on both sides. So now my equation V looks like this, is equal to mRT over PM. And once I have that equation, I get to plug it in. And I don't even need to convert the grams into moles, because it'll take care of it, which is kind of cool. So when I plug this in, actually, let me erase this real quick. It'll look a little like this, where I have V, my mass is 125 grams, and I didn't even have to convert that to moles, don't need to. My R, still going to use my 0.0821 atmosphere liter, and put my mole Kelvin down here. My temperature is still 273. My pressure is 1 atmosphere. Now, the molar mass, we solved for that, which was 46.01, but be sure that you put your proper units in there. And again, molar mass is grams per mole. So put the grams here, then the moles are on the opposite side of the equation. Okay? Now, check this out. Cancel out alike units. Atmospheres, gone. Moles, gone. Kelvin, gone. Grams, gone. What unit remains? Liters, which is your volume. And I guarantee you, when you type it in, you will get 60.9 liters, or something very, very close to that. So again, there's really 3 ways that you can work this problem out. And I don't care which way you use to work it out, just as long as you're showing me your whole process. Let's take a look at number 3. Number 3 asks, at what temperature will 33.4 grams of carbon dioxide have a volume of 1,750 milliliters at a pressure of 850 milliliters of mercury? Okay. So what we have here, and again, not a bad idea to do this, is that we want to identify our variables. So we have our grams, which will be our moles. We have our volume, which will be V. We have our pressure, which is P. And it wants to know at what temperature. Okay? So we have all of our variables, and the nice thing is we only have one set of variables. So that means that we're going to be using this equation, PV equals nRT. And since we're going to be using that equation, and we only have one set of variables, this makes it for a very nice problem. However, be sure, since we're using the variable R, we have to have all of our units in the same units as R. And in this case, the R that I plan on using is the 0.0821, and that's in atmosphere liter per mole Kelvin. So that means that all of my units need to be in those units. So I need to change the grams into moles. I need to change the milliliters into liters. And I need to change the pressure into atmospheres. And then we'll solve for the temperature, which is in Kelvin. Okay, so let's do that first. So the milliliters, pretty nice, 1750 milliliters. 1 liter, there's 1,000 milliliters. So really, you don't need to show that step, since I would hope that you all could swing the decimal over 3 places. So 1.75 liters. The pressure, 850 millimeters of mercury. You will be given this, conversion where 7.501 millimeters of mercury equals 1 kilopascal. And if you wanted to stop at kilopascals, that's fine, but I'm a big atmosphere fan. If you stop at kilopascals, be sure that you use the correct R for the kilopascals. So 101.325 kilopascals for 1 atmosphere, around 1.12 atmospheres. Okay, so we have our volume, we have our atmospheres. We also need to find out our number of moles, so we can convert our grams into moles. So we have our 33.4 grams, and that's of carbon dioxide, which is 12.01 plus 32, which is 44.01 grams per mole. Okay, so 1 mole is equal to 44.01 grams. So 33.4 divided by 44.01 is 0.75, we'll say 9. And that is moles. So now that we have our volume, our atmospheres, and our number of moles, now we can solve for T. So let's do that. And actually, I'm going to write my values down before I go crazy here. So my volume, 1.75. My pressure, 1.12. My temperature, or my number of moles is 0.759. Okay, so once I have that, all right, so now that we have our variables, we can move the variables around, and be sure to do that before you solve. So we'll have PV equals nRT, and we're solving for the temperature, which means that N and R are going to be divided on both sides. So now my equation looks like this: PV over nR equals T. And we can plug in our variables now. So the pressure, which is 1.12 atmospheres. The volume, which is 1.75 liters. The number of moles, which is 0.759 moles. And the R value, 0.0821 atmosphere liter per mole Kelvin. Okay. And then, of course, check to make sure your units can cancel out. Atmospheres are gone, moles gone, liters gone. What unit remains? Kelvin, which is your temperature. 31.45 or 31.5 is fine. And it is in Kelvin. Okay. All right, so again, on a problem like this, don't overthink it. Remember, hey, look at the variables that are given to you, or the values that are given to you, and determine what the variables are. If you have one set of conditions, you will use PV equals nRT. If it's not at STP, you will use PV equals nRT. And do recognize, we're not at STP. All right, number one, we're looking for the temperature. Number two, the pressure is not 1 atmosphere. Okay, so be aware of that. Number 4, A sample of chlorine gas has a volume, V1, 250 milliliters at a pressure of 245 kilopascals at a temperature of 70 degrees Celsius. What will be the pressure in atmospheres of the gas at 345, so T2, Kelvin at a volume of 3.44 liters, okay? Now I recognize and I realize these types of problems are your favorite. I get it, all right? Now, we aren't gonna have like the P1, V1 type equations. You have to be able to rearrange the variables from PV equals nRT, recognizing that we do have an initial set of conditions and a final set of conditions. So knowing that, let's look at what we have. So we have PV equals nRT, and you have an initial volume, you have an initial pressure, and you have an initial temperature, okay? Also, you have another set of conditions where you have you're looking for the pressure, you're given a volume, and you're given another temperature. So this is how we should be thinking about this. Now, whenever you're given something like this, make sure that the variable that you're looking for needs to be in the numerator or on top in your equation. So what we need to do is actually we need to rearrange variables so that the pressure still remains in the numerator. So if we were looking for temperature, we would divide both sides by P and V. But since we're looking for pressure, we need the pressure to stay on top. So we're going to divide both sides by T1. So now my equation looks like this, where I have P1 V1 is equal to NR, and that's over T1. Okay? You'll do the same thing for the variables for the 2's. Okay? So we'll get the equation that looks like this. P2 V2 is equal to T2. All right? So once you have your set of conditions, now we have to recognize we don't have any information in regards to the number of moles or the ideal gas constant, R. Nice thing is, we don't care. If they don't change, we aren't going to worry about it. Plain and simple. So now my equation simply looks like this. Okay. So I have my equation that looks like that. And then, since we're looking for P2, what that means is I need to divide volume on both sides, and I need to multiply temperature on both sides. And that actually is T2 and V2 that I need to do respectively. So once I have that, then my variables look like this, or my equation looks like this, where I have P2, because it's standing all alone, is equal to P1 V1, P1 V1, and we multiplied T2 on both sides, which canceled it out. So T2 there, and we have T1 on the bottom, and we have, let's see, V2 on the bottom as well. Okay. Now, be sure that you're actually labeling so that we don't do something dumb when we do this. Typically, what people do is they'll flip the temperatures, or maybe even flip the volumes, because you're careless in that regard. Take care of the variables. Know which is which here. All right. However, since we have the equation set up like this and we're not using R, we don't have to have the same units as the R value, okay? So we don't have to have it in atmospheres. We don't have to have it in liters. The only thing we have to have is the temperature, which is in Kelvin. So we have to change the 70 by adding 273. So add 273 to that, which gives us a new temperature of 343. Okay, so we have 343 Kelvin, and let's see, the other temperatures are already in Kelvin, so we're good. Our volume is in liters here, and milliliters here. We have to have alike units there, so it's just easier for me to move the decimal to there. So now my new volume looks like this. Okay, so 0.25 liters instead of 250 milliliters, and now everything's the same. My pressure's already in kilopascals. Don't trouble, leave it alone. All right, so now that we have that, let's go ahead and plug these in. I'm going to erase this to give us just a little bit of room to work with. Okay. So here's how our equation is going to look. So P2 is equal to P1, which is 245 kilopascals. And as a heads up, the unit that you're looking for better have a representative of it in the numerator. If you had the P in the denominator, you have everything inverted. I guarantee it. So make sure that you do have a representative on top, because we need that unit on top because we're looking for pressure. All the other units are going to cancel out. All right, then V1, go back to the question, that's V1, not this one. So we're going to plug in our 0.25 liters. Our T2, and this is where a lot of people make mistakes because they go, oh yeah, no, T2's over here. So 345 Kelvin. And then our T1, which we solved for here, 343. And the volume V2, right here, 3.44. Looks like that. Now, just to double check units, always show your units in all these steps. Okay, so kelvins, gone. Liters are gone, and that's the only units that we can cancel out, so we're left with kilopascals, which again is a pressure unit, so we're in great shape. So we can solve for this now, and that's 17.9 is our answer. And since we're in pressure, it's kilopascals, so kPa. Okay. So again, be aware of where your units are, especially in the problem, and then place them in the correct spot. But be sure, the minimum that I need to see for a problem like this is right here. But some of you may need to show more. In other words, I think in the homework, I identified each of the variables along the side, and I noticed that while a lot of you are working at the problem, you still do that. I think that's excellent. Some of you, this might be enough. Especially if you write neatly enough that you can actually identify those variables. Either way, it's fantastic. But what I have in the bubble, that is the minimum. All right, let's look at question number 5. Question number 5 asks, what volume of fluorine gas is needed to react completely with potassium to form 298 grams of potassium fluoride at a pressure of 164 kilopascals and a temperature of 35 degrees Celsius? All right, a couple things that we need to start recognizing. Number one, is this a stoichiometry problem? The answer is yes, because we have fluorine gas and we have potassium, and it forms potassium fluoride. That right there tells us that we have a stoichiometry problem. Next thing we need to ask ourselves is this a limiting reactant problem? Well, it's asking for the volume of fluorine gas needed to react. Ooh, that tells us we don't have a limiting reactant problem because we're looking for one of the reactants. Okay? So first of all, step one, let's write out the balanced equation. So we have fluorine gas, and again, ends in INE, so that means it's diatomic, F2, needed to completely react with potassium, potassium's K, to form 298 grams of potassium fluoride. Potassium has a +1 charge, fluorine has a -1 charge. So we're good as written there. So I'm going to write above there 298 grams, just so I don't forget that. Also, it says that we're looking for the volume, so question mark V there. All right. And let's see, so it says at a pressure, so here's our pressure, and a temperature of 35, so 35 plus 273, so 308 Kelvin. And again, be sure that you change your temperature to Kelvin, is our T there. Okay. So we have our reactants, we have our product, we have all the information, and actually we don't need to go back to the problem since we have everything right now. All right, so step one, is that balanced? Well, we have 2 fluorines here and only 1 there. So that means I need a 2 there, and I also need a 2 there. Okay. We don't know anything about the potassium. Better yet, we don't care about the potassium other than balancing it for the equation. Okay. So now that we know that, now we need to do our work here. So looking at this problem here, we start off with 298 grams of the potassium fluoride. Since it's a stoichiometry problem, take what's given, or start with what's given. That will get you moles. The temperature and the pressure are not enough to get us moles. The grams are enough to get us moles. So we'll take the 298 grams of potassium fluoride and be sure to convert that into moles. So 1 mole of potassium fluoride. And again, the potassium is 39.1 grams plus fluorine is 19. So our molar mass is 58.1 grams. Okay. Now, since we are not at STP, we can't go one more step, okay, and change it to our volume of 22.4 liters. However, we do need to go one more step and change the moles of potassium fluoride into moles of fluorine. So we'll place our moles of potassium fluoride at the bottom here and the moles of our fluorine on top. What values go in each of these? Well, there's a 2 for our potassium fluoride, and there's a coefficient of 1 in front of our fluorine. We need to find out how many moles of the fluorine we actually have there. So we can type that out. So 298 divided by 58.1. And then we're also going to divide that by 2. So I get 2.56 moles of my fluorine. So now I have my N value. So now that I have my N, okay, I have my N, I have my P, I have my T, I can now solve for my V. So I will write out my equation. PV equals nRT. And since we're looking for the volume, that means that we need to divide pressure on both sides. So now my equation looks like this, where I have V is equal to nRT over P. And we plug in the values that we just solved for, so 2.56 moles. The R value that we'll use here, since we are in kilopascals, we need to use the 8.31. kPa, liter, that mole Kelvin down below. The temperature is 308, which we found earlier. And the pressure is 164 kilopascals. Okay. And then we just solve. So our volume, and again, of course, look at your units. Moles cancel, Kelvin cancel, kilopascals cancel. You're left with your liters, which is volume. So we have our volume, and the correct volume is 40. And we'll say it's just 40.0 liters. Okay. And again, with this stoichiometry type problem, we need to balance the equation, start with what was given, convert what was given into moles, use the mole ratio to get rid of our moles of potassium fluoride to get our moles of fluorine. That gives us our moles of fluorine. Now we can plug it into our equation and solve. Number 6, if 45 grams of nitrogen reacts with 125 liters of hydrogen at the same temperature and pressure, what is the mass in grams of the ammonia produced? All right, we have 45 grams of nitrogen, so let's go ahead and write that down first. We have nitrogen, 45 grams. We have hydrogen, which is 125 liters. And the question wants to know what mass in grams, question mark, grams of our ammonia is produced. Okay. Based on this, do we have a limiting reactant problem? Yes, we do. So we have 45 grams and 125 liters. So what we need to do is make sure, number one, we balance the equation. So is that balanced? No, we have 3 hydrogens here and 2 here. So there are 3 there, a 2 there, and I believe we're balanced now. All right, now, since we do have a limiting reactant problem because we have 2 initial amounts for our reactants, we need to find out which one of these will be consumed totally before we can calculate the ammonia. Show the limiting reactant step. In other words, the limiting reactant step compares reactants to reactants. We don't ever want to calculate for how much product we have until we know how much of the, or which one of these is a limiting reactant. So, and it doesn't matter which one you pick, just pick one. Okay? So, I'm going to be a devil's advocate here and picked 125 liters. So, and again, it doesn't matter. So if I start with my 125 liters, okay, and it says we're at the same temperature and pressure on the test, I'll make sure that I say that that's at STP. But we'll say that it's at STP for the sake of this and to speed it up just a little bit. So we have 125 liters, and it's at STP, so that means that 1 mole of the hydrogen has a volume of 22.4 liters. So if I were to stop right there, actually let's put a unit on there, so that's H2. So if I would stop there and tell me how many moles of hydrogen I have, I need to use the mole ratio to get to moles of nitrogen. I'm going to go moles of hydrogen here, moles of nitrogen here. Then from the balanced equation, I'm going to put my values in. So I'll have a 1 there and a 3 there. And again, that's the only time that I use the coefficient is in my mole ratio. How do I know I'm using a mole ratio? I have moles over moles. It's the only time I'm going to do it. That's another reason why we need to show what it's moles of. Now, from here, we need to go one more step and get it to the units that the problem has given it to us in. So we're not going to write 22.4 up here, but we're going to change our moles into grams. So nitrogen has a molar mass of 28.02, which is 14.01 times 2, 0.01 grams. And then we need to solve to find out. My answer here is 52 point, we'll say 1, and that's grams. Okay? So based on this information here, pause the video for just a second and ask yourself, or try to determine which one of these is the limiting reactant if you don't know already. All right, so you've had a chance to think about it. So here's how you need to talk yourself through this. If I used all 125 liters of my hydrogen gas, I would need at least 52.1 grams of my nitrogen. I only have 45. So for me to use all 125 liters, I need 52 grams. I don't have it. I only have 45. So my limiting reactant in this case here is my nitrogen. That is my limiting reactant. In other words, my nitrogen will be consumed totally before I have a chance to use up all the hydrogen. Okay? So once I've done that, now I can solve and answer the question. The question wants to know what mass in grams of the ammonia will be produced. So I'll start with my 45 grams of nitrogen. Change that into grams, or I'm sorry, into moles. So again, that's 28.02 grams. And then use the mole ratio, so moles of nitrogen 2 moles of ammonia, NH3. And again, the mole ratio in this case here is we have 2 ammonias and 1 nitrogen. And then my desired unit, or step 4, is to find out the number of moles. So 1 mole of ammonia is equal to 14.01 plus 3 times 1.008, which is 17.034 grams. And once we calculate all of that, we get a value of around 54.7. So 54.7 grams of ammonia. Okay. All right. So really, that's not a whole lot different than what we did before spring break. The only thing really that's new is right here with the 1 mole equals 22.4 liters. And again, that can only happen at STP. Okay. 7. Potassium chlorate, when heated, decomposes into oxygen gas and potassium chloride. If 84.3 liters of oxygen gas is produced at STP, what is the mass of the KClO3 required for this reaction? All right, so we do have this, so let's go ahead and write it down here. Produces oxygen gas and potassium chloride, okay? Now, the question wants to know what mass, so question mark grams, what mass of KClO3 is required to do this reaction if 84.3 liters of oxygen gas is produced, and again, at STP. All right, so do we have a limiting reactant problem here? No, we do not. But we do have a stoichiometry problem, so we still need to balance this out. So we have a 2 there, a 3 there, and a 2 there. Also, the nice thing is that we are at STP, which is very, very helpful in solving problems like this. So again, we can start with the 84.3 liters of what it is that we start with. Since we don't have a limiting reactant problem, there is no limiting reactant step. Okay, so we need to convert the liters into moles. So since we are at STP, let's use our 22.4 liter shortcut. And again, this is for our oxygen. So we need to now go to our mole ratio because we need to solve for the potassium chlorate. So the oxygen and our moles of KClO3. And from our balanced equation, we'll have 2 there and 3 there. Now the final step wants us to go back to grams. So 1 mole of potassium chlorate has a molar mass of 39.1 plus 35.45 plus 3 times 16. So the molar mass is 122.55 grams. And what's nice is, that's all we need to do for this problem and solve for that. And that is grams. Okay. So really, that one shouldn't be too difficult either. Number 8. And I'll be willing to bet that a lot of you have been waiting for this problem, or anticipating this problem. When it says the root mean square speed, the equation that you'll be using for this is, we have the radical, 3RT over big M. Okay. Couple things to remember about this equation. Number 1, the R value here is 8.31 joule over mole Kelvin. The other thing that we have to recall or remember is that a joule is equal to a kilogram meter squared per second squared. So yes, it is a conversion within an R value. Since we're talking about root mean square speed, we're talking about energy associated with that. So we have to substitute it in. Now, the reason why we have to have this unit here is because this molar mass is not in grams per mole, but it's in kilograms per mole. So we have a lot of things going on here that's not very typical for what we've been working out. So these three components we have to put into play whenever we see a problem like this. All right, so let's go ahead and do that. So let's reread the question. So the root mean square speed for sulfur dioxide, and again, sulfur dioxide is 1 sulfur, which is 32.06 grams per mole, plus 2 oxygens, which is 32 grams per mole. So sulfur dioxide has a molar mass of 64.06 grams per mole. Remember, the molar mass needs to be in kilograms per mole. And I would highly recommend that you show this step so that you don't do something dumb. So we need to convert grams into kilograms. Kilograms is bigger, and there's 1,000 grams. So that means that our molar mass, okay, actually let me just start that down here. Let me put the R in here, so 831 joule mole Kelvin. And our molar mass, which is 0.06406 kilograms per mole. And again, try to use only one division line there. And the temperature on top, we have 225, so 225 plus 273 is 498 Kelvin. Okay. All right. Now, if you were to stop here and solve for the value under the radical, you would lose some points, because what we're going to look for is a rate or a speed unit. Joule is not going to be the correct unit. And also, when we cancel these out, moles will cancel, Kelvin will cancel, but you'll be left with joule over kilograms, which doesn't make any sense, especially if you take the square root of those units. Now it gives you joule, the square root of joule over the square root of kilogram. That makes no sense. So what we need to do is substitute the joule, and you can do that automatically. You can automatically substitute the joule if you don't want to do that based on what we've been doing in class. So what I would do is rewrite this. So we have our 3 and 8.31. Instead of the joule, we're going to have kilogram meter squared and again, we'll have our 498 Kelvin, and that's still going to be over our mole Kelvin here. However, in addition to the joule, we also have second squared. So what I have in red is a substitution for our joule. 0.06406 kilogram per mole. And now we can cancel out alike terms. Okay? So the mole is gone. The Kelvin is gone. The kilogram is gone. So the units that we have left are meter squared over second squared. And again, when you take the square root of meter squared per second squared, you're left with just meters per second, which is nice. So let's go ahead and solve for this. This is giving me a value, and actually, I'm going to erase this. Okay, so now what I have under the radical is 193,805, And again, that's meters squared per second squared. Okay. So if we take the square root of that, square root of the answer, now I get an answer of 440 meters per second. Okay. So again, take your time, make sure you're using the correct values for each one of these. This is probably one of the more interesting problems, but again, the hardest part of this whole problem is the substitution of our joule for kilogram meter squared over second squared. Okay. All right, number 9. Number 9 asks you to calculate the density of decaying gas in grams per liter at negative 45.3 degrees Celsius and a pressure of 75 atmospheres. First thing is, let's take care of that. That negative 45.3 is not going to be good. So add 273 to that. And that gives us a temperature of 227.7 Kelvin. Our atmospheres are good, so we're good with that. All right, density. Using the equation, PV equals nRT, and substituting PV equals little m over big M, RT. Okay, we need to set it up this way. Again, what we're looking for density is mass over volume. We have to show that. Okay, so we need to rearrange some variables. And what we need to get is the mass over the volume. Okay, so the first thing I need to do, I'm trying to get these variables so that we have M and V all by itself. Well, I know that my mass has to stay here. So I need to divide R and T on both sides and multiply the molar mass on both sides. So I'm dividing R and T on both sides and multiplying molar mass on both sides. So now my equation looks like this, where I have MPV divided by RT is equal to little m. Okay? So we've got all of those over there. Now I need to divide volume on both sides so that my equation now looks like this, where I have MP over RT is equal to little m over V. So once I have that, now I'm ready to dance. But first, before we do that, we need to find out what big M is. So we need to find out the molar mass of our decane. So 10 times 12.01 plus 22 times 1.008. And the molar mass for this is 142.276 grams per mole. Okay, so once we have that, we're in pretty good shape. All right. So let me go ahead and erase that so we have some room to work. Okay. So we can plug in our values here. So MP, so our molar mass is 142.276, and that's grams per mole. Okay. Be sure that when you do molar mass, it's grams per mole. Okay. And then the pressure, what is the pressure here? 0.75 atmospheres. Okay. The R that we'll use is the 0.0821 atmosphere liter. And I'm going to erase RT here. Put the mole Kelvin right there. And the temperature, what is the temperature? We found it 227.7 kelvins. Okay, now let's find out what our units are that remain here. All right, so moles, gone. Atmospheres, gone. Kelvin, gone. And the units that remain are liters and grams, which is a mass over volume unit. So we're in great shape. Okay. So now we can solve, and it gives us 5.71. And again, that's grams per liter.